everyone, welcome again. So today's lesson will be on the metals topic of Year 11 chemistry. And in particular, we'll be looking at mole calculations. So in the last lesson, we looked at what the mole was. And in this lesson, we're going to look at more practical ways of using it and how we actually calculate things in chemistry. So this is the one, for those who aren't so confident in maths, to really focus on. So remember the formula that we looked at in the previous lesson? It's the number of moles equals the mass of our sample, what we measured, divided by the molar mass of the chemicals in that sample. Okay. So again, we'll cover more. We'll actually do a problem on this, and you'll actually see how it works. But that's just our equation. And if you burn it into your memory, that is really helpful because there's only a couple of equations in chemistry, and this is one of them. Just be wary that the units of m is in grams, and the units of the molar mass is in grams per mole. Okay, so if you get kilograms of sample, then you need to convert that back into grams. Okay, it really should be in kilograms for SI purposes, but historically we just use grams per mole. Okay. So again, we're going to just quickly touch on why use the mole. Well, the mole is a central unit in chemistry, and it's important for heaps of reasons. And the main one is that mass is often hard to compare because the chemicals weigh different amounts in terms of their actual molar mass and their size. So for instance, here we have hydrogen and here we have helium. Now they're right next to each other on the periodic table, but you can see that in terms of mass, they're going to be very different. This one's almost 4 times as big as this one. So that's why mass is not often used in chemistry to relate chemicals reacting with one another, because very huge things can react with very small things. And so mass is not a great way to see which one's being more used or less used than this mole concept. So here's how we solve any mole problem, okay? These 5 steps will basically give you the answer all the time. So take note, firstly, you always take note of any data that you're given. So mass of a chemical, how much they weighed it as, volume of gas that they released, anything like that. Just take note of it. Okay, write it down somewhere. That's useful. Next step is always to write out the chemical equation. Of course, unless it's given to you, then just look at it, make sure you know what it is. But in the reaction, when they tell you that something is reacting with something else, write that equation, because that will help you solve the question almost assuredly. Then look up the relevant molar masses on your periodic table. So once you know the reaction, look up any of the chemicals in that reaction and note down their molar masses. And that way you'll have all that data ready to go when you need to solve the problem. Calculate the number of moles of any substance that you were given the mass for. Okay? So if they say, I weighed out this much chemical, then calculate the number of moles of that chemical. Okay? That will again help you, because that number of moles is going to be related to the number of moles of other chemicals through number 3, okay? Through number 2, the chemical equation. And again, I'll show you how that works. So just be wary of all of these steps. And lastly, using the answer from 4, so that number of moles that you calculated, and the chemical equation from 2, work out the number of moles of all the other chemicals in the reaction, okay? So you can do that because they're all related by those stoichiometric coefficients. So those numbers in front of the chemicals in the chemical equation will help you relate the number of moles of one chemical to another. Okay. So just bear these in mind as we go through the examples, and you'll see how they all put together and how they work. So here's our first example problem. So say you were given 40 grams of magnesium and 32 grams of oxygen gas, and you asked to react them together, and this is the equation. 2 magnesium atoms for every 1 oxygen molecule gives you 2 magnesium oxide. Okay. So this is our equation. I'm giving it to you in this case, but many questions will ask you to write it out, so you're lucky, I suppose. Which of the 2 chemicals do you think you'll have in excess? Okay, so you've got 40 grams of magnesium, 32 grams of oxygen. Which one will you have left over after the reaction has finished? Okay. So let's see if we can work that out, and maybe the answer might surprise you if you're not if you're easily surprised, I suppose. So if you look at the equation, 2 moles of magnesium are required for every 1 mole of oxygen gas. Okay? So we need 2 moles of magnesium for every 1 mole of oxygen gas in order to get this reaction to go fully. Okay? Now let's work out the number of moles of each substance. So the number of moles of magnesium, so we have the mass of magnesium is 40 from the question. So we're taking note of all these things in our this data that they're given. So M of magnesium is 40. And now we look through our periodic table and we look for magnesium. So it's in group 2. So if you look down through group 2, you'll see it. And you'll notice that the molar mass is 24.31. Okay? And if you do the calculation, you get 1.645 moles. Okay? Clear? So now let's calculate the moles of oxygen. So oxygen gas. So there's 2 oxygen atoms. So we got 32 grams of it from the question. And if you look at the molar mass of O, it's 16, but there are 2 of them. So 16 times 2 is 32. And so that's our molar mass. And so we have 1 mole. All right? So we have 1 mole of oxygen. Now, there are fewer moles than necessary of the magnesium to consume all the oxygen. So the oxygen will be in excess. Okay? Surprising because the mass is less, right? But that's why the mole is so useful, because see how the mass doesn't tell you anything. It just tells you that there's a little bit more in terms of its weight. But here you see that because there's not enough moles, because we need, for every 1 mole of oxygen, we need 2 moles of magnesium. So there's not 2 moles of magnesium here. So we can't use up this whole 1 mole of oxygen. So that means that we'll have some oxygen left over after all the magnesium has been used. Okay? So that's why I like to use moles, or that's why chemists use moles, because the mass really doesn't tell you anything. So here's another example problem. So a student reacted sodium carbonate with calcium hydroxide and got a precipitate out. They weighed the precipitate and found it to be 5.6 grams. So here's the first thing. What is the precipitate likely to be? So keep in mind you've noted all this mass and things like that. So whatever comes out, we know it's 5.6. So now we're going to go to step 2, write the chemical equation. So sodium carbonate is Na2CO3. Okay? Because so the valence of Na is +1. The valence of carbonate is -2. So we have so in order to get 0 charge, we need for every 1 carbonate ion 2 sodium ions. So you just double check that if you don't know why that is. So you should be given that valence. And we have calcium hydroxide. So we saw this from the previous lesson. The valence of this is +2. The valence of this is -1. So we need for every 1 of these, 2 of these. Okay? So what is going to be the precipitate? Well, we probably just switch them around. Okay? So switch these two around, and we'll get the precipitate. So it's calcium carbonate and 2NaOH. Okay, so that's all we're doing. We're just switching them around, and that's what usually happens in a precipitation reaction. But again, don't worry too much. As you learn more chemistry, all of these things will become clear to you. There's our reaction, okay? So like I said, they switch them around, and this has become the solid, okay? So calcium carbonate. And we know it's solid because we've seen it. When you blow carbon dioxide through lime water, which is this guy, you get that precipitate, and that's where it comes from. Okay? So that's our precipitate. Just remember that. That's our precipitate. Now, it's calcium carbonate. So calculate the number of moles of this precipitate. Ooh, okay, so now we're going back to the moles topic. So we know that the mass is 5.6. So here's our equation. The number of moles of calcium carbonate is the mass of calcium carbonate divided by the molar mass. Okay? We know this one, it's 5.6. And we can calculate the molar mass of calcium carbonate, which we did in the previous lesson, but we'll do it again. So you can see that there's a carbon, which is 12.01, calcium, which is 40.08, and there are 3 oxygens, which is 16 times 3. Okay? And that's, remember, you just add them all together, and that's how we get it. And so this is the final number, 100.09, for the molar mass. And so now we just do that division, and we get the number of moles, 0.0559. That's the total number of moles. Okay? So hopefully you saw how to get the molar mass, and hopefully you saw how to work out this final answer. Okay? So what are some other applications of the mole? Well, the mole can be used in heaps of other areas of chemistry. It's used to work out the concentration of solutions. That's a particularly important one. One that I study very frequently is gas mixtures. So when you mix 2 gases together in combustion reactions and things like that, you have to use moles. You can't just use mass. So that's one I study. And the mole is quite relevant in pretty much any area of chemistry that you can think of. So don't think that it's just this little isolated topic. It applies to nearly every aspect of chemistry. So that concludes today's lesson on calculating the mole. So stick around because the question segment will be very, very important in helping you to understand how to use this mole calculation. So we'll move on to that now, and hopefully you can do it yourself, but if you need some guidance, this is why this video is here. So this is a very complex question, so don't be too scared. We're going to go with a very complex question because I have faith in you. So fertilizer can be made from ammonium sulfate, and here's the equation for that. A student weighed out 32 grams of the fertilizer, which has this in it. So if the commercial fertilizer contains 10% of this, ammonium sulfate, calculate the percentage by mass of ammonium in the fertilizer. Okay? So 10% of the mass of a fertilizer is this guy, but what mass of the fertilizer is just the ammonium? Okay? That's our question. So the mass of the ammonium sulfate we can work out very easily because we know that we took 32 grams of fertilizer and we know that this is only 10% of its mass. So 32 times 10% gives you the mass of the ammonium sulfate. Okay? 3.2 grams. Right? Now, we always do this. We always calculate moles because that's what chemistry is all about, calculating moles. So the number of moles of ammonium sulfate equals the mass of the ammonium sulfate over the molar mass. Okay? So we know the mass of the ammonium sulfate. So now we've got to work out the molar mass, and it's quite a hefty one too. So let's look at the ammonium first. So this guy here. So nitrogen is 14.01, and there are 4 hydrogens, so it's 4 times 1.008. So that's where your periodic table comes in handy. So just have that handy so you can see it. And then because there are 2 of them, we multiply that whole thing by 2, because in total there'd be 8 hydrogens and 2 nitrogens. So you can see that that would actually work out, right? And then we work on the sulfate. So sulfur is 32.06, and oxygen is 4 times 16. So there's 4 oxygens, and each one is worth 16. So that's where we get that number from, okay? And so there's our final number, 132.144. Okay, and then when we do the division, use your calculator, you'll get 0.0242 moles. Okay, you see that? Now, if we look at the actual molecule of ammonium sulfate, we can see that there are 2 moles of ammonium for every 1 mole of ammonium sulfate. So this is from the first lesson. We're counting, right? So what we do is we say, well, every one mole of this gives you 2 moles of the ammonium itself. So the ammonium is 2 times the number of ammonium sulfate moles, okay? So from the last part, we calculated that. So now we just multiply that number by 2, and that's our moles of ammonium. Then we want to work out its mass because we want to get a percentage of this. So let's work out its mass. So we rearrange the formula. So instead of N equals M on double M, we just multiply this way. So we get m equals n times mm, and that's where we get that equation from. We're just rearranging the formula. So we can say that here's the moles, and here's the molar mass of ammonium, 14.01 times 4 plus 4 times 1.008, because we worked that out in the previous part of the question. And then that gives us 0.8738 grams, right? Then the percentage is simply just divide the mass of the ammonium by the mass of the fertilizer and multiply by 100. So we know how to work out percentages. And that gives us this equation, which gives us 2.7%. Okay? That's how we work out. It's a very complex question, so I nearly say some year 12 students would struggle with this. So if you can work through it, then you're doing very, very well. Okay? So we'll move on to the next question. So question 5, a company wants to make an ethanol-powered car. So ethanol is a fuel. And it's competing against these octane-powered cars, octane also being a fuel. So what we have to do is we have to write balanced equations for each combustion process, assuming that we only have carbon dioxide and water as the products. Okay? So we already did in the previous lesson the ethanol reaction. So we did this exact process in the last lesson. So if you want to see that done again, just watch that video, which is the previous mole one. So here's the equation. We have ethanol plus 3 oxygens gives you 2 carbon dioxide plus 3 waters. You can work that out based on the fact that you know this, and you know that carbon dioxide and water are the only products. All you have to do is balance it. So, but I will go through the octane combustion reaction for you so you can see how to balance octane, and then hopefully you'll get an idea of how to do all these balancing equations, things that we have to do. Okay, so we have C8H18, that's our fuel. We're going to react it with some oxygen, and we're going to get CO2 plus H2O. And for those who are watching or who followed my lessons previously, you'll notice that I always put a lot of space between each of the chemicals, and as I go through this, you'll see why. So just bear that in mind for a second. So we'll first balance for carbon. So I always balance in this order: carbon, hydrogen, oxygen. So we balance carbon first. There's 8 on this side, 1 on this side. So how many times does 1 go into 8? Well, it goes in 8 times. And you see that there's 8 here, 8 times 1, which is 8 here. Okay, so we're balanced. Now you see that hydrogen appears in one part of this left-hand side and one part of this right-hand side. So it makes it very easy to balance. But when you look at oxygen, there's oxygen here and oxygen here, but only oxygen here. So you see that it would be much harder to balance, and because these numbers will keep changing as you balance hydrogen. So that's why we balance hydrogen next, because it only appears once on either side. So there's 18 on this side, and there's 2 on this side. So how many times does 2 go into 18? It goes in 9 times. And so now we have 18 here, 9 times 2, and 18 here. Okay, balanced. So what we're left with is the oxygen. So we have 8 times 2, which is 16, 9 times 1, which is 9. So 16 plus 9 is 25. So we have 25 oxygens on the right-hand side, but now we have only 2 on the left-hand side. So how many times does 2 go into 25? Well, it actually only goes in 25 on 2 times. So if you see that, 25 on 2 times 2 gives you 25, and we have 25 on this side, so we're balanced. Okay? Don't worry if there's a fraction. That's perfectly okay, because it's not saying that there's 25.5 oxygen atoms. What we're saying is there's 25.5 moles of oxygen. So so we're not actually talking about each molecule. We're talking about moles of a particular molecule. So don't worry about these fractions. You can use them, and that's fine. And you can see why I left so much space, because I wanted to keep filling in these numbers, because I didn't know what they were going to be before. So that's how we know. That's how we leave ourselves a bit of space so it doesn't get too cluttered. Okay? And if we look at our equation, there it is. Same equation. moving on. So compare the number of moles of oxygen required for 1 mole of each fuel. So in each equation we had 1 mole of the fuel, and you notice that there was, in the ethanol case, there was 3 moles of the oxygen, and in the octane case there was 25 on 2 moles of oxygen. Okay? So 1 mole of ethanol requires only 3 moles of air, where 1 mole of octane requires 12.5 moles of air. I'm remembering that 25 on 2 equals 12.5. Okay? So if you just didn't quite link up those two numbers, it's a little nicer to write 12.5 rather than 25 on 2. Okay? So the octane requires more than 4 times as much oxygen than 1 mole of ethanol. So that's a pretty cool advantage of ethanol, is that it uses a lot less oxygen. So we always get complete combustion, which is nice. So now we have a last question. If 3 grams of ethanol was injected, calculate the mass of oxygen required for complete combustion. So now we want to know how much oxygen we actually need to burn a certain amount of ethanol. Okay? Now, remember, we always take the same steps. We look at the equation, we look at the question, and we look at all the data that they give us. 3 grams of ethanol. Okay, that's good use. That's good data that we can use. So next thing is we calculate the number of moles of ethanol, because we know how many grams of ethanol we have. So here's our equation. So the number of moles of ethanol is equal to the mass of the ethanol that we've got divided by the molar mass. And remember, we look up these numbers here from the periodic table, and these numbers, these multiples, we learn from here. Okay, so the molar mass of a single of carbon atoms is 12.01, and you can see there's 2 of them, so we multiply by 2. This is the molar mass of hydrogen. There's 6 of them, 3, 5, 6. So 3 plus 2 is 5, plus 1 is 6. So we multiply by 6. And there's only 1 oxygen, so we get 16. Okay? So as we move along, we add them all together, we get 46.068. And then we get 0.065 moles as the number of moles of ethanol. And then we look, remembering from the chemical equation that we did before, we know that for every 1 mole of ethanol, we need 3 moles of oxygen. Okay? So that means that the number of moles of oxygen is equal to 3 times the number of moles of ethanol. So there's that. So if we multiply this by 3, we get 0.195 moles of oxygen, and that's our number of moles of oxygen. But now that we have the number of moles, well, what can we do with it? How do we turn that back to mass? So we want to know this little m at the top. So for those who are very math savvy, you'll see that m equals molar mass times n. So we're just multiplying this across, and you see that that will give us the m. So you can see that's the equation that I just showed you. So now we know this number. We need to find this number from the periodic table, and then we're done. So 0.165 is, 0.195, 195, there's a 9 there, is the number of moles of ethanol. 16 is the molar mass of oxygen atoms. And because there are 2 oxygen atoms per oxygen molecule, we have to multiply by 2. And so that gives us the final answer of 6.24 grams. Okay? So that's how we use moles to calculate various things. And you can see this is quite an industrial and practical application of using the mole. So that concludes today's lesson on practical applications of the mole. We looked at lots of questions and lots of ways to use the mole to calculate things. And I've given you a lot of very difficult questions to study, and many of them will be difficult even for Year 12 students. So if you can manage them, then you're doing very, very well, and you shouldn't have a problem once you reach Year 12. So I look forward to seeing you at our next lesson.